Okay, so the next thing that we want to show is that the interarrival times of a Poisson distribution are exponential. Before we can start talking about uh, what an exponential is, I at least want to cover, uh, I guess, trying to explain an interarrival time being exponential. The first thing I want to talk about is what an exponential distribution is, just in case you guys forgot from your statistics classes. So if a PDF of an exponential, so this is like sort of an the drawing or the graph of a PDF of an exponential. Um, so this is the PDF. This is the f of x. It's the distribution or the density function. So it's alpha e to the negative alpha. So most people use lambda, just so you know. I mean, most of the time you'll see lambda here or mu. You'll see that as well. I'm using alpha because I'm trying to connect it back to the Poisson distribution where most people use alpha as far as the rate. So if we get this as the probability density function, then what I want to do, the first thing I want to do is I want to show what a CDF is, right? So I'm going to calculate this probability, right? So I'm going to calculate the probability underneath here. And so we're going to let that be X. And so what I'm going to do is I'm going to find the probability that the random variable X, in this case, I didn't describe it, but the random variable X is distributed as an exponential alpha. And so random variable X is less than or equal to some value, right, which is the on here. And so we're trying to find all the probability underneath that curve there. So what is that? That is the integral. And what we have to do is we got to put this X on the limit of integration, because if you kind of look at this PDF, you can see that it's 0 up into this particular point. So there's no probability when it's negative. And then after 0, it starts at 0 and goes to this X. And then what we're going to do is, instead of using X here, because I can't use X in the limit of integration and in the integrand, so we're going to use what's called a dummy variable. We're going to integrate this thing out. So it'll be e to the negative alpha to the y dy, where y is just a dummy variable. After we integrate and substitute our limits of integration, it'll go away. And so it's just alpha 0 to x of e to the negative alpha y dy, and keep going. So when I take the antiderivative of that, I get 1 over negative alpha e to the negative alpha y. Let me make sure, take the derivative of that, negative. Okay, yeah, so that should be it. And then that's equal to, so just negative e to the negative alpha y, evaluated from 0 to x. And I probably should have put that here as well. Okay, so that you just don't forget it. And so we got that sucker. And so if I do that, I get negative e to the negative alpha x minus, right, because you subtract, and then minus a negative e to the, when I put 0 in here, I get negative 0. I just get 0 there. And so that's equal to, this would be minus a negative is 1, and then minus e to the negative alpha x. So this would be our CDF, or the probability that the random variable x, oh, that's a horrible x. The random variable x is less than or equal to some value x, right? So that is the CDF when x is greater than 0. So if I was going to write this sucker out, I would say the probability x is less than or equal to x is equal to capital F of x, right? So we use that because we, in calculus, generally you go from small f to big F when you take the antiderivative. And then that's just equal to 1 minus, here, let's just do it like this, 0 when x is less than 0, and then 1 minus e to the negative alpha x when x is greater than or equal to 0. So if I'm equal to 0, 1 minus 1, okay, yeah, that makes sense. Okay, all right, so this would be my CDF. This is what I'm aiming for, right? So I want to find that the Poisson distribution is related to this CDF somehow, right? So that's the intent of this video, and I don't know how long this is going to take me. I want to start off with this random variable w. And what we're saying with w is I'm going to let it be the time needed for one event to occur. And so that'll be, so if I wanted to write its CDF, it would be the probability that the random variable w is less than or equal to W is equal to, you know, I don't know if you guys remember all the things of probability here, but I can reverse this and put a greater than sign here just by doing 1 minus, just because all the probability has to add up to add up to 1. And then what we're saying by saying this is something I think a little neat. It's basically, this means that so look at the way we define the random variable. It's the time needed for one event to occur. And what we're saying is this amount of time, this random variable is greater than W. So this means that exactly how many, if I had a class here, means that exactly how many occurred so far up to W, it means 0, right? So nothing's occurred. So if W is the first time that some event occurred, that means nothing occurred in that window so far. So 0 events occurred up to that time in time W. I apologize for having to clear my throat so much. Or a better way to say this is if I let the random variable X be the number of events, in W, that, oh, by the way, is Poisson process governed by this Poisson process with alpha, then X must be distributed as a Poisson, and then alpha times, instead of alpha T now, W is the time, bad W. Alpha W is now, so W is that little time window that we're talking about now. Okay, so if that's the case, then I can now rewrite this as a 1 minus the probability. So this idea of W taking the amount of time that the very next thing happens is the same thing as saying that that X is equal to 0. Right, so the same amount of time that we're talking about over here is equal to that. So I can now write I can now write a probability because I know how this thing's governed. I know that it has a Poisson process, and I know sort of exactly what that sucker looks like. So I can now go 1 minus, what is this, lambda, I'm sorry, not lambda, alpha W to the 0 power, right? Because that's the X, and then e to the negative alpha W all over 0 factorial, right? Because I know that. And then if we do the simplification of this, it's 1 minus e to the negative alpha W, right? Where W is the amount of time. Oh, by the way, you know, this thing right here that we just showed is, and I wish I had it on the same screen, is actually the CDF of the exponential distribution, which means that W, this random variable W, is distributed as an exponential alpha, right? So that's really what we're trying to say here. And that's really the purpose of this video. I didn't want to go, I'm not going to go too much further into it, other than to state this one sort of final thing is this is very nice, right? So this ends up being a very nice result. So I will write this out. So the time that it takes for the next event, that it takes for the next event to occur in a Poisson process with rate alpha is known as an interarrival time. And again, these are pretty important. And these interarrival times, IAs, are distributed as an exponential and whatever the rate is. Okay, so that's what I wanted to get out there. Again, you might have to worry about, I shouldn't say again because I haven't really talked about this. So you might have to worry about how this parameter is described. In some cases, it's going to be alpha, and in some books, you'll find out that they will describe the exponential distribution as this. And so I don't care either way, but they'll use 1 over lambda e to the negative 1 over lambda x. And so you'll see that as well, you know, when x is greater than or equal to 0 and 0 otherwise. So you'll see this in some books or some cases, and in other ones you'll see it like this. You just got to kind of know what they're talking about and be able to sort of describe. And the reason why they do this, I believe, is because because this is actually the mean. It's 1 over lambda, and they want to describe it in terms of the mean. Other than that, I don't really know why people do it differently. But anyway, you got to kind of know. And I think, and I'm not sure how NumPy does it. We'll talk about that in class. Just because I don't remember, you know, it's been a long time since I've done that. Okay, so again, in class we'll talk about how to do that, and hopefully you got something out of this. And that's all I got for this one. We'll talk about the memoryless property of exponential distribution in the very last video.